Welcome back to Calculus 1. I'm Dr. Jeff Groh, and this is your integration lab. On this lab, question 1 states, state the definition of the definite integral. The definition that I would like you to give is the integral from a to b of f of x dx is the limit as the norm of the nth partition goes to 0 of the sum as k goes from 1 to n of f of ck delta xk. This general form of the definition allows for variable interval widths, the delta xk, random sampling points within each of those intervals at which you evaluate the heights, and we'll have a sequence of partitions that are finer and finer, refining the partition to the point where the maximum subinterval width tends to 0. That way we don't have a gap, refining other intervals, always leaving one large. They all have to get small. The largest subinterval must go to 0 as we refine our partitions. On problem 2, you're asked to use a Riemann sum to estimate the integral from 0 to 2 of x squared dx. Use right-hand rule and slash endpoints. What value is obtained with n equals 1000, and then using the second fundamental theorem of calculus, what is the exact value? To evaluate the Riemann sums, we need the x values, f of x values, and n and delta x. The x values start at 0. The function value takes the x values and squares them. We're going to start with n equals 8. Delta x will be the length of the interval, which is 2 minus 0, divided by the n value that we've chosen. To get to the new x, we take the old x and we bump over a delta x. The delta x, you'll recall, needs to be an absolute reference, so it needs dollar signs around the d. The function values are just calculated the same. Now I need to drag this down until I get to 2. That's going to be here. The way that we estimate these integrals is we take function values at right-hand endpoints and then multiply by delta x all the way down. So what we can do is we can come down here and do an auto sum from home. We'll do auto sum. We'll have to change this from B3. And then we need to multiply by the contents of the cell D2 where we had our delta x. And that gives us an estimate for the integral of 3.1875. You'll remember that the exact value can be found by the fundamental theorem of calculus. An antiderivative is x cubed over 3, evaluated from 0 to 2 gives us 8/3. So the exact value is 8 divided by 3. That's a fair bit different from 3.1875. So let's use a different value of n. Say n equals 1000. Let me undo what we've done, pasting all of this stuff down. I'll change this to 1000. Now I don't want to just drag this down to the row 1002. What I need to do is hit Control G. That's the go-to
function in Excel. And I want to go to cell A1002. So there I am. That's where my insertion point is now. I need to drag the different contents that I have in the cells A3 and B3 down. So I'm going to position my cursor over B3. Then I'm going to press the Shift button, and then I'm going to click, and that highlights all the cells down below. To force the computation down through all of those intervening cells, I need to press Control D. So I'll go down to the bottom now by dragging the scroll bar, scrolling down to the bottom. We'll do the same computation we did before. We'll hit the auto sum and change B2 to B3. And then we'll multiply by the contents of the cell D2. Now that's a far sight better than what we had before. Still not perfect, but at least it's in the ballpark now. You can see that using these right-hand endpoints, the convergence will be fairly slow, but we'll get there.
The exact value is very easy to find. We find an antiderivative using the power rule. You evaluate at the endpoints and subtract. You always plug the top value in first. The answer is exactly 8/3. On problem 3, I ask you to integrate the integral from 1 to 3 of x cubed plus 3x squared plus 2x plus 1 dx, using the definition of the definite integral. In step 1, we'll calculate delta x. The formula for delta x is b minus a over n. b is 3, a is 1. So delta x is 2 over n. Second, we calculate the partition points. X sub k is going to be a plus k times delta x. A in this case is 1. We have k times delta x, that's going to be 2k divided by n. And then finally, the integral. Will be the limit as n goes to infinity of the sum as k goes from 1 to n, f of x k delta x. This uses right-hand endpoints and equally width subintervals in the partition. In this case, we have the limit as n goes to infinity of the sum as k goes from 1 to n. F of xk is going to be 1 plus 2k over n cubed plus 3 times 1 plus 2k over n squared plus 2 times 1 plus 2k over n plus 1 all times delta x, which is 2 divided by n. The 2 over n can come out of the sum, but not out of the limit, since the limit is on n. So we'll have the limit as n goes to infinity of 2 over n times the sum as k goes from 1 to n. Now we need to FOIL out everything within the braces. A cube, x plus y cubed, according to Pascal's triangle, is x cubed plus 3x squared y plus 3xy squared plus y cubed. This gives 1 plus 3 times 1 squared times 2k over n. That's 6k over n plus 3 times 1 times 2k over n quantity squared. 2 squared is 4 times 3 is 12 k squared over n squared plus 2k over n cubed. That's 8 k cubed over n cubed. And then plus 3 times 1 plus 2k over n quantity squared. When we square this, we'll square the 1 and then multiply by 3. We'll take 1 times 2k over n times 2, that's 4k over n times 3, that's 12k over n. And then 2k over n quantity squared, that's 4 times 3 is 12, k squared over n squared, plus 2 plus 4k over n plus 1. If we combine like terms, we'll have the limit as n goes to infinity of 2 over n times the sum as k goes from 1 to n of 1 plus 3 plus 2 plus 1 is 7. 6k over n plus 12 plus 4, that's 22 k over n. 12 plus 12 is 24 k squared over n squared, and then 8 k cubed over n cubed. Simplifying, we have the limit as n goes to infinity. We'll write this as following: bracket 1 over n, the sum as k goes from 1 to n of 14. On the next term, we can bring the 22 over n out of the sum. That'll give us 44 over n squared times the sum as k goes from 1 to n of k. On the third term, the 24 over n squared can come out of the sum. That'll give us 48 over n cubed times the sum as k goes from 1 to n of k squared. And then the 8 over n cubed comes out, giving us 16 over n to the fourth, the sum as k goes from 1 to n of k cubed. End bracket. We have 3 formulas that I have asked you to memorize. When we add a constant, 14, to itself n times, we get 14 times n. Times 1 over n, we still have the limit as n goes to infinity, but all that's left on this first term is 14. On the second term, we'll have 44 over n squared times. Now the formula for the sum as k goes from 1 to n of k is n times n plus 1 over 2. On the next term, we have 48 over n cubed, and this sum is n times n plus 1 times 2n plus 1 divided by 6. And then 16 over n to the fourth times n plus 1 over 2, quantity squared, close bracket. Now we're ready to evaluate those limits. The limit of 14 is, of course, 14. We'll have a quadratic in the second term over a quadratic. N times n plus 1 over n squared tends to 1. So this term goes to 22. On the next term, we have a cubic over a cubic. When you take the limit as n goes to infinity in such a situation, you take the ratio of the leading coefficients. We're going to have 48 times 2 divided by 6. Well, 2 divided by 6 is 3, and 3 goes into 48 16 times. In the next term, because of the square, we'll have a quartic divided by quartic. 2 squared is 4. That goes into 16 4 times. So we have 20 plus 22 is 42, plus 14 is 56. We can check this result using the fundamental theorem of calculus. We find an antiderivative using the power rule for antiderivatives on each term. You plug in the 3 first. 3 to the power 4, well 3 squared is 9, and square that, you get 81. 3 cubed is 27. 3 squared is 9, plus 3. We subtract what we get when we plug in 1. That's 1/4, plus 1, plus 1, plus 1. 1 plus 1 is 3. We're subtracting that from 3. 81/4 minus 1/4 is 80/4, which is 20. Plus 27 is 47, plus 9 is 56. Okay, so having you calculate a definite integral like the last one using the definition might be a little mean. However, I wanted you to see that even for very simple problems like integrating a polynomial, the definition goes down bad roads, and there's a great benefit to using the fundamental theorem of calculus. The fundamental theorem of calculus is definitely your friend. On problem 3a, I ask you to integrate 1 over 1 plus x squared dx. That's the one. That's the one I wanted you to memorize. The answer is the arctangent of x plus c. On problem 3b, x over 1 plus x squared. This is not the one. And the reason I juxtaposed this next to the one I gave you in part A is I wanted you to see that very small variations in a problem lead to big differences in the answers. In particular, this is almost in the form f prime of x over f of x. These problems always have a very simple solution. It's always log absolute value of f of x plus c. And if you don't understand that, I'll show you why. We can do a u substitution. U equals f of x, in which case du will be f prime of x dx. Encapsulate that and put it in a little box. The integral is then transformed as the integral of 1 over u times du. Well, that's the log of the absolute value of u plus c, but you can't stop there. You have to substitute back for x. That gives you log absolute value of f of x plus c. Anytime you see an integrand of the form f prime over f, you can jump directly to this answer. Now that's not quite what we have on this problem, but it is almost. The derivative of the denominator is 2x, not x. But remember the old Spanish proverb, take what you want, then pay for it. I want the numerator to be 2x, so I'm going to make it so. I'll pay for it by putting a 1/2 in front. Now the answer is 1/2 log absolute value of 1 plus x squared plus c. You may jump directly from the question to this answer. On 3c, I give you the integral of x plus 1 over x squared plus 1. This is a kind of mixture of the last two problems. And we can break the fraction into pieces. X over x squared plus 1 dx plus the integral of 1 over x squared plus 1 dx. This gives us 1 times the log of the absolute value of x squared plus 1 plus the arctangent of x plus c. Easy as that. On part 3d, I give you the integral of 1 over the square root of 1 minus x squared dx. That's the other one that I asked you to remember. You get arcsine of x plus c. On part E, I give you the integral of 2x plus 2 over the quantity x squared plus 2x plus 3 to the power 8 dx. If the power 8 were not here, this would be in the form f prime over f, but it's not, so we must use a u substitution. You do see the derivative of something lying around. U is going to be the thing that has its derivative lying around, so that du will be 2x plus 2 dx. The integral is now transformed as 1 over u to the power of 8 du. This may be rewritten as u to the negative 8 du. And now we may apply the power rule for antiderivatives. That gives us u to the power negative 7 over negative 7 plus c. We need to substitute back for x. So I'll write this as negative 1 over 7. The negative exponent means shove it across the division symbol, so we'll have u to the 7 in the denominator. U is x squared plus 2x plus 3. That will be raised to the power of 7, and then plus c. Don't forget the plus c. You don't know how many times I've had students screw up a problem just like this on the exam. You should study this problem because you can be reasonably assured that there will be one like it. On part F, I give you the integral of e to the x over e to the x plus 2 dx. The derivative of the denominator is e to the x. So this is in the form f prime over f. We simply write down the answer. Log of the absolute value of e to the x plus 2 plus c. That's it. On part G, we have the integral of the sine of 7x dx. You should know the answer is minus 1/7 cosine 7x plus c. But let's suppose that you didn't know that because you forgot that you're supposed to divide by the 7 when you calculate these integrals. We can still use a u substitution. We could try u equals 7x so that du is 7 dx. I have the dx but not the 7, so I'll have to divide the 7 off. We have 1/7 times the integral of the sine of u du. The integral of sine is minus cosine, so I'll have minus 1/7 cosine of u, but u is 7x plus c. On part H, we have the integral from 0 to pi over 2 of the cosine of 2x dx. I wanted you to see something kind of special on this one. Anytime we have the cosine of omega x, the period is 2 pi over omega. In this case, the period is 2 pi over 2, or just pi. And I wanted you to think about the geometry here. If the period is pi, then half the period occurs at pi over 2. And if we were to integrate this graph from 0 to pi over 2, you have to get 0, just based on geometry. We don't even need the fundamental theorem of calculus here, though we could use it. I wanted you to pick up on this. We're going to use this a lot in Calculus 3. Of course, you may use the fundamental theorem of calculus if you don't pick up on the geometric trick that I just trained you. I might be a little disappointed, but I can't mark you off. An antiderivative will be minus 1/2 sine of 2x evaluated from 0 to pi over 2. That gives you minus 1/2 the sine of, well, 2 times pi over 2 is pi, minus 1/2 the sine of 0. Sine of 0 is 0. Sine of pi is 0. The sine of any integer multiple of pi is 0. So, just as before, the whole thing is 0. On part I have you integrate from 1 to 5 x times the square root of 2x squared plus 4 dx. I see the derivative of something lying around, more or less. Looks like a job for a u substitution. U is the thing under the square root, 2x squared plus 4, because du is 4x dx. I have the x dx, but not the 4. So I'll divide that off. The integral is transformed. The new lower limit of integration will be 6. If x is 1, then u is 6. If x is 5, 5 squared is 25 times 2 is 50, we'll have 54. The x dx goes away to become du over 4, and then we get u to the 1/2 du. We may now use the power rule for antiderivatives. We'll have u to the 3/2 times 2/3 evaluated from 6 to 54. We can cancel a 2 and get 1/6. Now, whenever you take a number and raise it to the power of 3/2, that is that number to the power of 1 plus 1/2, or a root a. So we'll have 54 root 54 minus 6 root 6. There is a little bit more simplification that can be done. 6 goes into 54 9 times, and we can cancel the 6 on the second term. 54 is 9 times 6, so we're going to get 9 times the square root of 9 times 6 minus the square root of 6. The 9 could come out as a 3, that'll give us 27. 27 root 6 minus 1 root 6 is 26 root 6. On part J, you might think I'm pulling one over on you, but I'm not. I'm trying to teach you an important principle. You might say, oh, I'll just change the limits of integration on the last one. But it's easier than that. You should say, this one is obviously 0. And the reason it is that the integrand is an odd function. That doesn't mean that it's peculiar. That has a very specific meaning and an important geometric implication, so that whenever you integrate an odd function from negative a to a, you will get 0. How can you identify this as odd? You need to know what it means for a function to be odd, and that doesn't mean that it does inappropriate things in social settings. F is odd if f of negative x equals negative f of x. That's true here. Let's set f of x to be x times the square root of 2x squared plus 4, and calculate f of negative x. we'll have negative x square root of 2 times negative x squared plus 4. The negative x squared has a negative that goes away because you're squaring it. The negative out front can be detached, and you get negative x square root 2x squared plus 4, and that is minus f of x. Therefore, this function is odd. What does that mean geometrically? At negative x, you get the negative of what you had at x. Whatever you have at x, at negative x, you get the opposite. So anytime you integrate from negative a to a, an odd function, you have to get 0. You can tell by looking at this now. The integrand is odd. The negative gets squared away here, and one negative pulls out. Anytime you have a negative that pulls out of the function's odd. On part K, I give you the integral of secant of x dx. Now, you're supposed to remember that that's the log of the absolute value of secant of x plus tangent of x plus c. But let's suppose you didn't remember that. There was a garbage can calculation that I dragged you through. Remember? The garbage can calculation went like this. Take the secant of x, multiply by secant of x plus tangent of x over the same thing. As long as you're multiplying by the same thing top and bottom, you're not changing the value of the integrand, only its form. We'll distribute, but we'll reverse the order of the terms in the numerator. We'll get secant of x tangent of x plus secant squared of x, still over secant of x plus tangent of x. At this point, you're supposed to notice that the derivative of secant is secant tangent, and the derivative of tangent is secant squared. The integrand is now in the form f prime divided by f. We immediately deduce that the answer is log absolute value secant of x plus tangent of x plus c. On part L, I give you the integral from 0 to pi of cosine squared of x dx. This won't be 0 because the integrand is a perfect square. You have to get something non-negative out of this. The point here is that you should remember the half-angle identities. Cosine squared of x is 1/2 times the quantity 1 plus the cosine of 2x, and sine squared of x is 1/2 times the quantity 1 minus the cosine of 2x. We have 1/2 times the integral from 0 to pi of 1 plus the cosine of 2x dx. On the second term, you're supposed to recognize that the period is 2 pi over 2, or pi. And if you integrate cosine over an entire period, you must get 0. If you integrate a constant on some interval a to b, you get the area of a rectangle. The constant that you're integrating is the height. The length of the interval is the width. So the area is k times b minus a. In this case, we have 1 times pi, and then times 1/2. The answer is pi over 2. On part M, I give you the integral from -2 to 2 of the square root of 4 minus x squared. What I'm hoping that you'll recognize is that the function y equals or minus x squared, if you square both sides and move the x squared over, you'll see that you're dealing with at least a portion of a circle of radius 2. Because we're using the principal square root, this has to be the half disk from minus 2 to 2. This gives us 1/2 the area of the disk. The area of the disk is pi r squared. So our answer is 2 pi. On part n, we're integrating from 0 to pi sine squared x dx. Do you remember what to do? You need to use the half angle identity. Then, the period is pi, and you're integrating over a full period. So the second term contributes nothing to your answer. Geometrically, the answer is pi over 2. On part O, you're integrating 1 over x dx. You're supposed to just remember that the answer is log absolute value of x plus c. But you can also see this from the fact that the integrand is in the form f prime over f. On part P, I give you the integral of 1 over x natural log of x dx. You see the derivative of something more or less lying around. That means we need to use a u substitution. U is the thing that has its derivative lying around. In this case, the natural log of x, so that du is 1 over x dx. Using this substitution, the integral transforms as 1 over u du. You can see that we can break this off into 1 over log of x times 1 over x dx, and that transforms exactly in this way. We'll get the log of the absolute value of u plus c, and then substituting back log absolute value of the natural log of x plus c. We're now at the last problem in this review. I'm asking you to find the integral of the tangent of 2x dx. You need to rewrite this as the sine of 2x over the cosine of 2x dx. Now, the derivative of cosine of 2x is negative 2 times the sine of 2x. We're missing a negative 2. So if I put a negative 2 here and a negative 1/2 out front, the answer is negative 1/2 log absolute value of the cosine of 2x plus c. But let's presume that you didn't understand that. If you didn't understand that last method, you can surely understand that we can use a u substitution here. U equals the cosine of 2x, so that du is minus 2 sine of 2x dx. The minus 2 can be divided off, and the integral transformed into minus 1/2 the integral of 1 over u du, which gives us minus 1/2 log absolute value of u plus c, or minus 1/2 log absolute value of the cosine of 2x plus c.